Imagine witnessing the exact moment when the invisible forces that govern all life on Earth finally reveal themselves to human eyes. That impossible dream just became reality, and it's about to change everything we thought we knew about chemistry. Researchers have achieved what many considered scientifically impossible, capturing a live-action movie of a single electron as it dances through a chemical reaction. This groundbreaking achievement, detailed in a study published on August 20th in Physical Review Letters, represents the first time anyone has directly observed the movement of a valence electron during the precise moment when molecules transform. But here's where it gets controversial. This discovery might completely overturn decades of chemistry textbook illustrations that show electrons as neat little balls orbiting atomic nuclei like planets around the sun. The breakthrough centers around something as common as household ammonia, yet the implications stretch far beyond your cleaning cabinet. Ian Gabalski, a physics doctoral student at Stanford University who led this remarkable research, explained that his team managed to photograph the actual electrons responsible for driving molecular motion during chemical reactions. For generations, scientists have been playing a frustrating game of hide-and-seek with these crucial particles. While researchers could successfully use ultrafast X-ray scattering techniques to capture images of atoms and observe their chemical transformations, there was always a critical blind spot. These powerful X-ray beams interacted primarily with core electrons, those tightly bound particles nestled close to an atom's nucleus, while completely missing the valence electrons that actually orchestrate the entire chemical dance. Think of it like trying to understand how a symphony works by only hearing the percussion section, while the violins, which carry the main melody, remain completely silent. We wanted to take pictures of the actual electrons that are driving that motion, Gabalski revealed, highlighting the team's ambitious goal to finally see the invisible conductors of chemistry's grand orchestra. The potential applications of this electron-watching capability could revolutionize multiple industries. Scientists believe that understanding precisely how valence electrons behave during chemical reactions could pave the way for designing more effective medications, developing environmentally friendly chemical processes, and creating materials with unprecedented efficiency levels. Ammonia emerged as the perfect molecular candidate for this historic first glimpse. Gabalski described ammonia as kind of special because its composition consists primarily of lightweight atoms. This unique characteristic means fewer core electrons exist to create interference, giving researchers their first real opportunity to detect signals from the elusive outer electrons. The experimental setup required the extraordinary facilities at SLAC National Accelerator Laboratory's LINAC Coherent Light Source, a cutting-edge facility capable of generating incredibly intense, ultra-brief X-ray pulses. The research team developed an ingenious two-step process. They first delivered a precisely timed ultraviolet light pulse to the ammonia molecule, causing one electron to jump to a higher energy state, a transition that naturally triggers chemical reactions when electrons abandon their preferred low-energy positions. Immediately following this initial excitement, the team deployed their X-ray beam to record the shifting electron cloud as the ammonia molecule began its breakdown process. And this is the part most people miss. Electrons don't actually exist as tiny, solid particles zipping around atomic nuclei like miniature solar systems. Instead, quantum physics reveals that electrons manifest as probability clouds, three-dimensional regions where finding an electron becomes more or less likely depending on the cloud's density at any given location. Higher density means you're more likely to see the electron, Gabalski clarified. describing these ethereal clouds that scientists call orbitals. Each orbital possesses a distinctive shape determined by both the electron's energy level and its position relative to the atom. To successfully map these ghostly electron clouds, the research team employed sophisticated quantum mechanical simulations designed to calculate the molecule's complete electronic architecture. These computational tools determine precisely how electrons populate the various orbitals surrounding any given molecule. The actual imaging process relies on the wave-like properties of X-rays themselves. As these high-energy waves pass through an electron's probability cloud, they scatter in multiple directions before interfering with one another, creating measurable patterns that contain hidden information about the electron's location and movement. By carefully analyzing these interference patterns, Gabalski's team successfully reconstructed detailed images of the electron's orbital structure and documented its motion throughout the chemical reaction process. The true validation came when researchers compared their experimental results against two competing theoretical models, one that accounted for valence electron motion and another that ignored it entirely. The experimental data aligned perfectly with the first model, providing definitive proof that they had successfully captured genuine electron rearrangement in real time. But here's what makes this discovery potentially controversial. If we can now directly observe the fundamental building blocks of chemical reactions, does this mean that much of our current understanding of molecular behavior has been based on educated guesswork rather than direct observation? Are we about to discover that chemistry textbooks need complete rewrites? The research team envisions adapting their electron watching system for use in increasingly complex, three-dimensional environments that more accurately simulate real biological tissues. Such advancement could bring this technology significantly closer to practical applications in regenerative medicine, potentially enabling scientists to grow or repair human tissue on demand by controlling chemical reactions at the electron level. What do you think? Will the ability to watch individual electrons transform how we approach everything from drug discovery to material science? Or are we overestimating the practical impact of this microscopic achievement?